Great. Okay, so we're recording. Morning, everyone. Welcome back to our class on Wednesday, Reinforced Concrete Design. Now, we are doing this online synchronous mode. Has a lot of benefits. You can get easy access. You don't have to care so much about your appearances. And it's pretty convenient for you to follow. We upload the recording videos. Okay. Now, also, we may have some problem as well in terms of interactions. So to help facilitate interactions, I'm going to do some little meet and greet type of deal next week. But today, let me try to do this. I'm going to do a pseudo attendance check beside a Zoom link check I have. So if you feel convenient, you can open up the camera so we can see each other, and you can let the rest of the class know, who you are, that kind of thing. If you have some problem technically, you can try to use microphone just to speak so we know each other, okay? So I'm just gonna go by the list I have, okay? So Abdulaziz Alamari, do we have Abdullah here? Abdullah? Okay, I got Abdullah's not here just yet. Okay, how about Muhammad Al-Kabandi? Muhammad?
I'm here.
All right, good to see you. You might turn on your camera, or you're still in bed?
I will do next class.
All right, okay. Sorry, it's for the surprise, I guess. Okay. How about Abraham Al-Katan? Abraham. Sorry if I massacred your name. Abraham, are you there? All right. Abraham may not be here. Okay. How about Noah Ashman? Noah Ashman.
Yeah, I'm here.
Hey, how are you doing, Noah?
Good. How are you?
Good to see you. I like your cap. Pretty cool hat.
Thanks.
Dalton, Mr. Brown, Dalton Brown.
Yeah, I'm here.
Hey, how are you doing, Mr. Brown?
Oh, doing good.
Oh, I see. I like your name very much. I used to watch the cartoon, the Charlie Brown. I guess nothing to do with you, but anyway. All right, next is on the list. Bryce, Carapar or Cherapar. Sorry, did I butcher your name again, Bryce?
Yeah, it's Parker, but it doesn't say it.
Okay, sorry about that. Thanks, Bryce.
You're good. You're good.
Good to see you. Okay. How about Jacob Clemens? Jacob? He was here last time. Oh, he might be late. Let me check back with him to see if he's late or not. I see. John Crawford, Mr. Crawford.
Yeah, I'm here.
Hey, how are you doing, sir?
I'm doing great. How are you?
Good. Nice to see you. See, you guys all have good appearances, not like me. Much better than me, I guess. Okay, let's see. Wade, Mr. Compton. Wade Compton.
Yeah, I'm here. Good morning.
Morning. How are you doing, sir?
Doing good. How are you?
Good. Glad to see that. Well, you're ready, I think. All right. Tyler Frank, Mr. Frank.
Hello.
Hey, old friend. How are you doing, man?
I'm doing pretty good.
Good. Had your breakfast yet? Everything's fine, I guess. All right. Who's our next list? Jeffrey. Okay.
Hi.
Yeah, Tyler. Your internet is sometimes unstable. Okay, just so you know. Hey, Jeffrey, where are you?
Yeah, I'm here.
Oh, okay.
I have my camera on, but it's not working for some reason. I'm really not sure why.
Oh, no worries. I mean, it's not mandatory, but it might be good that we can have these interactions, I think, to solve the problem. Okay? Good.
Okay.
Yeah. Good to see you. Lucas, Mr. Kirk.
Yeah, I'm here.
Hey, how are you, man?
Good, how are you?
Good. A few more days, eh?
Yeah, a couple more and I'm out.
Okay. Not too bad. All right. Justin? Mr. Hackman? Come on, buddy. Where are you at? Mr. Hackman. Is he here? Justin. Hey, I saw you, Justin.
Hi, Professor Wu. How are you?
Good. Just say Bob or Dr. Wu. Don't say professor, not yet. 5 more years.
I apologize.
Don't worry, just kidding. So good, you're here. Adam Hark, Mr. Hark.
Hello.
Hey, how are you doing?
Good. How are you?
Good. Like your background.
Yeah, thank you. My room's a mess, so
Well, which software? You use Zoom, right?
yeah.
Oh, there you go. Much better. I like that.
Here we go.
All right, Austin, Horst Camp. Did I butcher your name, Austin?
Yes, sir. I'm here.
Oh, hey, how are you? Nice meeting you.
Good. Nice meeting you.
Seems like you like my class very much, right? Joined the last minute, I guess. Okay, so you're at the on campus, BCH building right now?
Yeah, I'm at BCH right now.
Okay, that's good to know. Well, be careful, right? So,
Probably should put my mask on.
sure, no problem. You don't have to do that. Just make sure. Okay, hey, good to see you. Regan? Miss Hubbard?
Hi,
Hey.
yeah, I just switched to desktop,
Okay.
and so I don't have a webcam for it right now, but I might be able to go on by next lecture. So.
Oh, no worries. I have a nice picture of you, but we call it dynamic. So like I always do that, right? Good to see you, yeah. Khalid, Mr. Malal?
Yeah, I'm here.
Man, you're like a DJ right now. I hear a lot of echoes. Yeah. You're home? Your camera's not working, buddy.
Oh, just a minute.
Uh-huh. Listen,
Oh, actually, I don't have.
Oh.
My camera is not working right now. Maybe I'm gonna try next time.
Oh, no worries, no worries. Yeah, I've heard a lot of your sounds, Mr. Khalid. I guess it's from your brother. Oh, just joking. All right. See you. Brett, Mr. Manager. Brett.
Hello.
Hey, how are you doing, man?
Good. How are you?
Good. Did I misspell your last name as usual? Can you say it again? Say it right, please.
Managry.
Managry. Okay, thank you very much, Mr. Managry. Nice meeting you.
Thank you.
Michael McKernan.
Yeah, I'm here.
Hey, how are you doing, man? Did I say your name right?
Yeah, it's McKernan. So.
McKernan. Yeah, I need a lot of corrections. I've been stuck in with my wife for the whole summer. Very few English, so I'm trying to get back on track, I guess.
Good.
All right, thanks a lot. Nice seeing you. Jack, Mr. or Miss?
Hey, I'm here.
Hey, how are you, Jack? Oh,
Good, how are you?
Good. Man, really lovely background.
Oh, thanks.
I like that. You just need a cup of coffee, right? I guess.
Yeah.
All right, good deal. Steven, Mr. Porosky. Steven, do we have you here, Steven? Oh, missing. All right, missing action. Okay, all right. Megan, Miss Proper. Megan.
It's Proper, but yes, I'm here.
Hey, nice meeting you, Miss Proper. Yeah. Oh, I see. You're pretty convenient, right? Just get up, I guess.
No, I just ran from BCH because my 8 a.m. professor ran late. So I was like, oh, okay, got a couple of minutes to run back to my house.
Okay, thank you very much. I'll probably create some 5 minutes pre-introduction like this every lecture, so to make it easier for all of us.
Okay.
Good seeing you. Yeah. Peter, Mr. Schenker.
Yeah.
Hey, how are you doing, man?
Pretty good. How about you?
Not too bad. Did I butcher your name as well? Last name?
Oh, no, you're good. Got it right.
Wow, all right. I feel like I'm winning a lottery here. Okay, that's pretty good feeling. Thanks.
Yeah.
All right, so Daniel, Mr. Steen. Daniel, where are you, buddy?
Morning.
Hey, morning. Oh, man, you're fully messed up. Like that. Double thumbs up. Oh, cool. So you're in BCH, I guess, I figured?
Yeah, I am.
Oh, okay. I see. Yeah, I might swing by later in the afternoon. Okay, good to see you. Yeah. Abdullahan Talib. All right.
Hello.
Hey, how are you, man?
All good.
Good. Glad to see you, man. For a minute.
Glad to see you too.
Okay, good to see you. Did I say your last name right? Talib?
No, it's Taylor.
Taylor, man, so horrible.
Yeah.
Thank you very much, Taylor.
No problem.
Good to see you. All right, so we have another Austin. Austin Witcher. Austin?
Yeah, I'm here.
Hey, did I say your last name right, sir?
You're close. It's Weicker.
Weicker. See, it's never close, but
Close enough.
Close enough. Thanks. All right, good to see you, Austin. Yeah, I like your team back there, Blues.
Oh, thanks.
I don't watch them too often now. I don't have enough time, but they are my favorite. Thanks. Benjamin Wood, Mr. Wood.
Hey, I'm here. How you doing?
You good? Are you, man? Your camera is not
Complain.
working.
Yeah, I'm all in the same situation as Reagan. I'm on my desktop and don't have a.
Oh, okay. I see. No worries. It's not mandatory, but maybe we can meet face to face next time, right?
That'd be cool.
All right. Thanks a lot. Good to see you. Marshall Woods. Miss Woods. Marshall, I see you here. Can you hear us? Yeah. Oh, sorry, Mr. Oh, man, this big mistake. Sorry about that. Mr. Woods. Okay, good. Where are you? Let me see if I can see you. Apologize for that. Oh, okay, you're driving. Man, pretty cool, eh? Are you going on campus or are you at home?
So I had to come back to Raleigh this morning and got stuck up in a couple things.
All right.
Yeah, figured I couldn't miss class, so now I'm like driving in class.
I like that. My master student Weston does the same thing. I tell you what, just turn off your camera, put me on the radio so you can hear it. Okay, I'm gonna make it like audiobook. Okay, so be safe. All right. Okay, good to see you, Marshall. All right, good deal. Okay. All right. Thank you all very much. Really appreciate it, man. So I see most of us are here. Trust me, I'm not trying to be a video blogger, which is pretty popular these days. I heard that they make pretty good money, much more than I do. Kind of jealous. Actually, I tried last semester. I put all my YouTube videos online. I thought that maybe I can put some commercials in it if it gets popular. But guess what? I only get one peak before the exam. That's as close I ever get to video blogger. So I hope this semester I make more exams, make more reviews, so my hit rates will go up. So eventually I'll be qualified for the commercial or whatnot. Okay. Joking aside, I just really encourage all of you to watch the video later. Okay, I'm recording this one. I'm gonna put it on the YouTube so you will see it later. Okay. All right. So let's continue our journey. Before we start the lectures, I just want to update several things. First of all, we still have some technical issues. Permission number. A few students I assigned permission number. The system gave me errors. I'm working with the department. There's some other professors have the same issues. So once I get addressed, you should be able to register. If you still have any trouble, just send a message and let me know. Okay. So if you don't see anything by tomorrow noon time, just send the email because I might have missed you. All right. Okay. So that's one. Second thing is I'm making the first set of homeworks. As you see from the syllabus, we have more percentage weighting for the homework than exam. So we might have a more content for the homework to make up the shifted percentage. Okay. So let me explain. If you haven't attended this class before, well, of course, well, I'm saying like if you haven't heard from your friend attending this class before, previous semesters, the exam are weighing 25% per piece. Okay, so 3 exams takes about 75% of your total score, and that's quite significant. So because we are doing this online synchronous version, we just shifted the percentage more to the homework. So now you see only 20% for each exam, so that adds up to 60%. But we don't want you guys to have free lunch, right? Nothing free these days. So we make the homework a little bit more comprehensive, but not for the purpose of punishing you or reduce your grades on that, but actually to help you prepare better for the exam. Okay, so you will see, oh, sorry, Al-Katan, okay. I'm sorry, you may have joined it late or I probably didn't see your name yet because I haven't on the list yet. Okay, let me make a note of that. Sorry about that, guys. One student just text messaged me. Okay. I got you here. Okay. Sorry about that. Okay. All right. So coming back to the weighting percentage. So we increase the number of problems to help you practice more, and this will prepare you better for the exam. Okay. Now, one thing. You guys have a lot of fraternity and sororities. I know you have a lot of friends who took this course before, and they must have a lot of information for you. Take them. They're very helpful. I won't say otherwise. And on the other note, do not try to copy the answer from previous semesters, okay? We make new homeworks every semester. Okay, so that is saying our homework this semester will be drastically different from last semester. So don't rely on that. Okay, one more note on the homework. I know you guys like to work in group. There are GroupMe and software, and especially with Zoom and all this online software, things are become easier for you to work in a group. I don't object that. I think that's a fantastic idea. Although there are some disadvantages working in group as well. For example, if one student he developed an answer, a lot of students just jump onto it. That's something I don't want to see. Or group homework become a group party. It is more talking and fun, less than working on the issue. That I don't like. All right. So you have to work efficiently to get the homework on time. All right. Last thing about the homework, it has to be turning on time. So this online thing actually help us to keep track of the time. I cannot alter the submission time. I will set a fixed amount. So this you have to submit by the deadline. Now there will be time we release the homework a little bit late because we have to readjust some numbers to make sure the answers are correct. If that happens, we will delay the release of homework, but you will have an extension for submission. That is every time you will have a full week to work on it. Okay, you will have a full week to work on it. So there shouldn't be any excuse to turn it late. If you have other reasons, you need to let me know, okay? And don't let me know the last minute, okay? Send me email like a day before, 2 days before, and let me know what's happening, okay? All right, that is all about homeworks, okay? So the other things we can talk along the line, and let's quickly get back to our course content here, which is design process. We left that from last lectures, all right? So we talked about the code honor, right? It is very, very important for us as a civil engineer to keep the design safe, all right? So we said, how do we keep everything safe? We need some criteria. We need some criteria to determine our structures intact or not. So there are 3 levels, okay? There are 3 levels. There's ultimate limit state, there's a serviceability limit state, and there's a special limit state, okay? And I just want to quickly summarize for you. When we say ultimate limit state, that means structure will fall down, okay? Structure will fall down, and we don't want that to happen, okay? And when we talk about serviceability limit state, that means the structure is no longer fit for usage in terms of excessive deflection, excessive cracks. Those are something we don't want to happen. After the last but not least, special limit state. Those typically require the building susceptible to wind load, earthquake, natural hazard, or marines or tide, all these special circumstances, okay? So these are 3 main categories, all right? And we talked about this last time. We mentioned that we don't want to happen. These are things we don't want to happen. For instance, loss of equilibrium. Say I have a column, I have a beam on top of it. Somehow, if I break the connection, it just falls down. It cannot maintain equilibrium. That's something we don't want to happen. Rupture, when we have a bridge that takes too much load, it just fractures in the middle. Something we don't want to happen. Progressive failure, progressive collapse means if one component is damaged and you don't have any redundancy in the building. Okay, if you don't have any redundancy in the building, means if this critical element is gone, the whole building is gone. I can give you a quick example. In the I-35 bridge 5 years ago, we have everything hinge on one rivet joint. Okay, we don't have any redundancy in that truss structure. What happens as corrosion occurs, we lost strength of that joint and the whole bridge is collapsed. Okay, so that's something we don't want to happen. And next on the line is formation of plastic mechanism. If you go to our structure lab, which is under construction right now, but if you go there sometime, you can see there are damaged columns, okay? And when the column is damaged, does not mean they totally lost their load-bearing capacity. Does not mean that, okay? Typically means is you can still sustain load, but you see a large shift in terms of deformation, all right? Large shift in terms of deformation, and that is called plasticity. That is called plasticity, okay? Instability, have you ever watched a lot of movies? Okay, have you watched a lot of movies? I do. There's a one famous movie, Pompeii, right? There's a huge city and nearby a volcano. When it's erupted, you see everything shaking. And they like to make the CG effect for a movie, right? The first thing you see building before collapsing down is what? They shake, right? They shake, right? What happens is when the ground shifts, the condition, boundary condition of the structure changes, and they are no longer stable. Means a tiny disturbance change in load will result in a total failure. all right? And that's what we call instability. That's what we call instability. And this, when this happens in a normal usage condition, this become a problem, okay? Become a problem. And last but not least on the list is fatigue. Fatigue, okay? We all know this. If we have a building standing there for 50 years, 100 years, things bound to happen. Why? Deterioration, fatigue, right? Loading, unloading, loading, unloading, create micro cracks that eventually eat out your building, okay? These are ultimate limit states, okay? Now, serviceability is very straightforward, right? Excessive deflection, we talk about it. Excessive crack width, we talk about it. Undesirable vibration, okay? Undesirable vibration. I want you to make a note here, okay? Because it may show up in the exam. What types of undesirable vibration they can have, right? One is when I have too much of a dynamic load, and the member is too slender. The rigidity is not big enough, okay? So when the rigidity is not big enough, you might have a soft member that can vibrate quite a bit, okay? That's one possibility. Second possibility, when your characteristic stiffness of the member is close to the resonant frequency of the loading condition. That means if you generate echo, okay? If you generate echo, okay? And when that happens, the vibration each individual member will reach its maximum and lead to collapsing, okay? And you may have heard about this before in the ancient military marching. When they march across bridge, it was prohibited or prohibited the military personnel will march in the same pace. Why is that? Because when they march in the same pace, they create this loading frequency that might synchronize with the frequency, natural frequency of bridge itself, and then may lead to collapsing, okay? So that's the undesirable vibration category, okay? Category, right? So the special limit states, okay? So we start talking about this due to earthquake. That means you have a ground motion, okay? Let me give you a simple, I have a simple question here. Maybe it can help you understand, okay? So we have a ground that moves, right? We have a ground that moves, okay? So I have three types of buildings. Same floor height, okay? Same floor height, I have three types of buildings. Concrete, steel, and wood. All right, let me repeat. So I have three types of building: concrete, steel, and wood. So under earthquake, which building will fall down first? Under earthquake, which building will fall down first? I'm gonna pick Megan. Can you take a guess? The concrete, the steel, and the wood building under earthquake. Which building you think is gonna fall down, collapse first?
Would it be the concrete?
Yes, that's actually the correct answer. There you go. But why? What's the reason? Can you provide some rationale behind it?
I would just think it's a structural like integrity.
It's rigid.
Maybe.
Yes, it sounds like it's integrity. It's like a box, right? It's rigid, right? It's rigid, right? It's not flexible enough, right? Yes,
Okay.
That's very close. That's the reason. So you think of it, when I have three types of structure, concrete is like a box. When I shake the ground, the whole thing will try to shake together, right? And there's no deformation induced by that. And with the limited deformation, all the energy will go into the material itself and break the concrete buildings, okay? For the steel structure, it is more slender. So the member allows certain deformation. So that will allow energy dissipation. So it will reduce the chance of falling down. For the wood, it's even better, right? For the wood, it's even better, okay? So we have more flexibility in the wood, okay? And has more deformation because everything's kind of loose. So the wood building, we actually tend to fall down the latest, okay? And that's why in Japan, okay, in Japan and South California, we have a lot of wood buildings. Okay? That's not like intentionally for earthquake, but part of the reason for it, okay? Good. Okay, so next, damage collapse due to explosion, fire, or collisions. And before 9/11, this is mainly from the oil tank, from the oil and gas industry. And now we actually have to build special buildings in terms of consideration for explosions and that kind of stuff, okay? And then structural effect due to corrosion or deterioration. This is very critical, okay? So in terms of reinforced concrete design, you won't have enough concrete cover to slow down the corrosion process, okay? To slow down the corrosion process. Last but not least, nuclear issues, okay? That's for radiation. So we have to build concrete nuclear safety shell, have a certain thickness of concrete, so the radiation will not penetrate through it. Okay? So all these, right, can be summarized in terms of strength and serviceability type of design, okay? Now, this course right now is focused on the strengths, which we'll talk about how we design for member force, composite actions, and for the member force, we talk about flexure. You can think of it as bending, so it's more tension controlled bending, and shear, which means we have a wall will go like this, or beam will go like this, breaking in half, that's shear. And last but not least, for column, we have a vertical member, I have an axial force, and bending force. Okay, so we are focusing on these three individual members for design purpose. Okay, all right. So before we go on, let's talk about the strength design requirements, okay, and analysis methods. All right. So first of all, this is our Bible, and you see that this is old codes 14. Right now we're on 19. Okay, right now we're on 19. Now I had a student ask me a question. So Dr. Wu, 14 is cheaper. Can I get 14? The answer is no. I use this image just to show you, but in reality, you cannot. There are differences in equations between 14 and 19. If you use 14, you might end up using the wrong equation, okay? So we're gonna use 19 for design, okay? And then for strength design requirement, what is the design requirement? Okay, so think about design, right? Think about design in the simple manner. I have provided strength, okay? That is design strength. Okay, so in the sense of design strength is what the strength I want the building to have, okay, by my calculation, all right? So provide the strength. And this strength has to be bigger than the required strength, okay? What is required strength, okay? So planning, I have 100 people staying on the floor. The building should hold. Now, this 100 people loading, external loading, is called required strength. It's called required strength, all right? So how do we maintain this balance? How do we ensure every time we design something is bigger than the required strength? We have to introduce two factors to ensure that, okay? What are these two factors? You see this a lot. One is called strength reduction factor. Strength reduction factor is to say that, okay, I design, I calculate the member will theoretically take so and so load. But I use a pre-multiplication member in front of it to reduce that, okay? So that is called the strength reduction factor. All right? Kind of underestimate the possible strength for the member. So I intentionally lower my expectation, okay? And required strength is to magnify, to exaggerate how much load is gonna sit on top of the floors. Okay, so you reduce your expected design strength, enhance your expected load strength, and still want to make sure this reduced design strength is bigger than the exaggerated load strength. All right, so quick question is, why do we do that? Why do we do that? Right, all right, so first of all, for the design strength, why do you think the actual member will have a lower strength than the design? Okay. The question is, we call names now. The question is, why do you think the actual member of the design fabrication will be lower than the theoretical strength, design strength we have? What would be the cause? What would be the cause? Okay, so I'm gonna go with Daniel. Daniel, are you there?
I'm here, didn't quite catch.
Okay. Can you try to answer, the quick question is, why do you think the actual member has lower strength than design usually? Why?
Why do I think the actual member has lower strength than design?
Right. Do you think it's possible, or if that's possible, why? Can you think of any reason? Say, we expect you to make a structure that is strong, but you go out and make it, and the structure is actually not strong. What can go wrong in the process? What can go wrong?
All sorts of things. It could fall down if you design it for more than it can hold.
So a lot of things, right? Specifically, right, let's talk about that's cranes. A lot of things can go wrong. Murphy's Law, right? So specific, what can go wrong? First of all, we have construction materials, right? You probably are taking construction material class. The material is a complex issue, right? You have design strengths, but maybe the material does not hit it, does not reach it, right? For example, we have construction itself has problems. For example, like alignment. When this column is supposed to sit right in the center of the site, it does not, right? Due to the crane operation, there are some errors, misshift, right? So that deviation from the design may cause a reduction of the strength. And that's human errors as well, right? You need to account for it, okay? So for the other side, loading factor the required strength part. Why do we need to apply load factor? Why do we need to apply load factor to exaggerate the anticipated service load? I'm gonna go call Jacob. Jacob, you there? So why do we have to make our required strength bigger? Why do we have to make our required strength bigger?
Because of the risk factor, I would assume, the threat to human life.
I'm sorry, can you say that again? You might have to cut closer to the mic.
Can you hear me?
Yes.
I would assume it would collapse. There'd be, threat to human life, I would assume.
Oh, okay. That's unexpected events, right? Unexpected events means we don't expect that to happen, but it happens, right? That's actually correct.
So you're talking about like the earthquakes and stuff like that?
No. That's similar. That's similar. But for the load factor wise, it's kind of similar, but a lower extent. What I'm trying to say is, for example, I designed for a building, for instance, for this floor. Originally, I designed for 50 people. Okay, but people who are using the building, they don't go out and check the maximum capacity. I mean, there's a sign of it, but not a whole lot of people check, right? We usually call in like 100 people. I don't know, right? Why? Because we have more people sometimes, right? So we have to prepare for that scenario to happen. So yes or no, your answer is right. There's going to be unexpected events, but that means the expected loading can fluctuate, right? The expected loading can fluctuate. Also, for example, was originally the building was designed for schools, for us to take lectures. But later on, maybe they decided to stuff in machines to turn into a factory, right? So they have to check and so on and so on. So we want to make sure we have enough flexibility, allow the load to fluctuate, okay? So that's the reason. Yeah, good answer, thanks. So now carry on. Stress requirement, load and resistance factor necessary because of variability, right? That's what we talk about, the resistance, the loading, the consequence of failure, okay? What is the consequence of failure? Now, let me say this, if it's a bridge, we expect it to be, or hopefully the bridge will never fail, right? Because the bridge fails, we have, trucks falling down and people get hurt, okay? But if we say I have a tool shed, just some structures that built up in my backyard, it fails, what's the big deal if I'm not in there? Just my tools got damaged, right? It gonna hurt me a little bit, but not as much as a bridge failure. So it depends on the importance of the structure, the consequence of failure, we have to change the factors. We have to change the factors, okay? So there's a guideline. Okay, now again, I have to change this to 19, I'm sorry, should have changed this before. But by 3.18.19 section, the section states saying 21.2.1, the stress reduction factor phi, okay, has to take account of the following reasons, okay? This will show up, let me say this will show up in your first midterm exam, okay? The first midterm exam, so please make a note of here, okay? So under strength of a member, that means the member is weaker than we expected when we design. Inaccuracy in the design equations. So when we design the equations, or when we design the strength of the member, we use design equations. Some of the equations are not accurate. There are a lot of empirical relationship from the equations, okay? Next, the degree of ductility and require reliability of the noded numbers. That means if I expect the member to hold, for instance, if the floor get weakened, all right? Let me make an example. If you walk down in the first floor in the BCH hall towards your survey room, okay? If you look up where you're crossing the survey room door, you see a giant crack there. I don't know whether they patch it or not. You can go back and see it, okay? that crack is safe, okay? That's not a damaging or crack that cause the failure of the building. But say if the member is very, very important and they will have a crack, that means we will have under strength, right? We also have to enhance the design strength to prevent this thing from happening, right? So that is something we have to account for when we do the stress requirements, okay? So all these 4 items that will show up in the exam, okay? So you want to pay attention to these 4, okay? All right. So what's the number, right? So is it a 5% discount, 10% discount, 20%? We need to get some number. We're engineers, right? So these are the strength reduction factors you will use for different scenarios, okay? So you see that phi is the strength reduction factor, depends on different loading situations. We have a tension control. That means the structure is mainly determined, the strength of the structure is mainly determined by the tension. We have compression controlled, which means the structure is mainly dependent on the compressive strength, okay? This is spiral, means I have hoop reinforcement in the column, okay? Or this circular reinforcement, transverse reinforcement in the beams, okay? And we have compression control we have shear and torsion, we have bearing, okay? So you see that as the list from top to bottom, top down, the phi is reducing, okay? Why is that? First of all, if we have a lower phi, okay? If we have a smaller phi, say 0.65, okay? If we have a lower phi, say 0.65, do we expect the building will have a low resistance or high resistance? Okay, so let me say in another way. Let me rephrase it, okay? If I have a phi equal to 0.65, which is lower than 0.9, okay, a smaller number, right? Do we over-design the building or are we under-designing the building? Do we make the building safer or make the building more dangerous? Who's next on our list? Austin Weicher? Austin, Mr. Weiger? Are you there or?
Yeah, I'm here. Sorry, I couldn't find my mouse. Oh, what was the question again? Sorry, I was writing down.
Oh, so when phi is a smaller number, okay, say 0.65, okay, so the smallest I have from the table, okay, we use this number for design. Do you think we'll make the building safer in comparison to use 0.9 or will make it even weaker or more dangerous?
I would think if it's a high or a lower number and make it more safer.
Okay, so lower number make it safer, right? So that means we anticipate this type of failure for the building will cause more reduction in terms of a design strength, isn't it? Isn't it, Austin?
Yes,
okay.
That's what I would assume.
Great, okay, like that, thanks, that's the right answer, okay? So yes, and why is that? The reason is you think of a bearing, shear, compression, all these are brittle failure, okay? Sudden failure. It means if that happens, there's no time for you to run. Once it fail instantly, right on the spot, okay? There's no residual deformation to hold the building together. Yet for beams, okay, if they fail, they go excessive deformation, they go on until your final failure, till the steel reinforcement ruptures, right? So that offers us time to run, okay? So that means it has higher ductility, okay? So the table shown here, actually reducing phi depends on the failure mode. If it's more ductile, you have a lower number, that means we have more confidence in the member that it will hold. But we have a lower number, means we have less confidence in that member will hold, okay? It's more critical, all right? So I just want you to understand this, okay? All right, good. All right, so after the stress reduction factor, okay? After you multiply your design strength with a stress reduction factor, okay? We call this nominal strength, okay? That is a strength of member cross-section calculated using assumption and strength equation of the strength design method, okay? So nominal strength, okay? And then load factor, okay? Overload factor due to probable variation of service load. We talk about that. And service load, there are loads specified by the general building code, unfactored, okay? So there are factored and unfactored part of the load. okay, which we're talking details, okay. So there are different type of load, okay. So there are different types of various types of loading for the structures. We have the dead load, okay. We have the live load. We have the roof live, snow, rain, wind, seismic, soil, fluid, temperature, creep, shrinkage, you name it, okay. So let me try to gauge ourselves with the meaning of this, okay. So Peter, Mr. Schenker, Peter, are you there?
Yeah.
Okay, so get ready for the next question, okay? This is for you, sir.
All right.
All right, so what do you think, okay, what do you think the dead load for a building mean? Like, what's the dead load for a building? I mean, give
Like objects that are anchored down that don't move.
okay, anchored down, don't move, right? For example, in the classroom setting, the desk and chairs are sitting empty there, right?
I mean, I feel like those could still be a live load because those can change.
I see. So HVAC.
Yeah.
I see. That's right. So that's a dead load. Okay. How about others? Besides that, what will be the other component of the dead load?
I'm not sure.
How about concrete itself?
What yeah, I guess.
Right. Self-weight, right? Self-weight, right? So self is also part of dead load, right? The materials itself, the gravity, right? Gravity that holds down, right? So you're right. So that's good answer, Peter. Thanks a lot. So dead load typically comprise or consist of the self-weight, and those permanent, let me say this, okay? Those permanently attached accessories to the building, okay? Like HVAC, okay? Like windows and the ceilings and all these are permanently attached to the building. These are something dead load, right? Okay, so my next question for Tyler. Tyler, can you hear me, Tyler? You stay there? Tyler?
Can you hear me?
Yeah. All right. So my next question for you, okay? So what do you think about live load? What are the live load? Let's just simplify in a classroom setting. What would be the live load for us?
People walking around.
Walking around.
Mostly, I guess. That's like your biggest live load inside of a building.
Okay. So people, that is mobile, right? Mobile load, and also equipment, right? Like desk, table, and chair, all that kind of stuff, right?
Yeah.
Right. That's a good answer. Okay. So now let me ask you guys this question. Do you think the dead load will have larger variation or the live load will have larger variation? And that goes to Reagan. Reagan?
Yeah, so I've been having some connection issues. Live load would have more variation is what I would guess.
Right, so live load will have more variations. Good answer, thanks a lot. So we want to consider all this in the design, okay? So we have to use different load factors for this. Say if I know concrete weigh 150 pounds per cubic foot, sorry, okay? Concrete weigh 150 pounds per cubic foot, okay? I'm going to use 1.2 for dead load. So I know that is 20% of variations, okay? 20% variation. But if I say people walk on the me, so for example, walking on the classroom floor, I'm weighing like 220 pounds. So that's my live load, right? I'm going to use 1.6 for variation, all right? Because I might lose weight over next summer, who knows, right? Put on my slim suit, everything, right? So that's 6%, right? 60%. So rule of thumb, always remember, whenever you see a dead load is 1.2. Okay, whenever you see a dead load, 1.2. Whenever you see a live load, 1.6. Okay, so when you do the load factors of 1.2 dead plus 1.6 live. Okay, now there are of course other type of loading: roof live, snow, rain, wind, seismic, soil, fluid, temperature, creep, and shrinkage. All these you can actually find from the code ASCE 7. All right, ASCE 7. Okay, you use that for your senior design. So the kind of preview. So by different loading, they will give a different factor. For this class, though, only the two we use most often: 1.2 dead, 1.6 live. Okay. All right. Good deal. Okay. So there you go. That's the ASCE 7 minimum design load for building and other structures. Okay. So if you're interested, please go and take a look at it. Okay. All right. Now here are the strength requirements. Strength requirements. All right. So see, there's different equations, right? You said, Bob, you just said 1.2, that 1.6 lying. Look at this table equation. You're crazy, right? So many equations other than just the one you mentioned. Yes. Why is that? It's because in different scenarios, okay? If this building is for residential, you have one combination of load. If the building is for transportation, for bridges, you have one combination of load. If the building is for us, for teaching, education, that's a different combinations, okay? And all this will be specified for you during the design purpose, okay? Now, the most used case for us is actually number 2, okay? Equation number 2 here, okay? So let's see if I can highlight it, okay? So this is most usage equation for us. It's always 1.2 dead plus 1.6 live, okay? So that's what we're gonna use for the first homework. We're gonna use that, okay? All right, good deal, okay. So now, required strengths, okay? What is required strengths? So think of it, right? If you reach the maximum capacity of a member, okay? If you reach the maximum capacity of a member, basically you build something, you take to the lab, you break it, right? At that breaking point, okay? At that breaking point, you get some number of resistance, right? And these are the required strengths. These are the required strengths, okay? So it has a subscript U to represent the ultimate, final, okay? Ultimate. So MU is a factor moment, required factor strength, right? So it means I need to have this much of the strength for this member, okay? So it won't break down, okay? PU, factor axial force, okay? VU, factor shear force, TU, factor torsion moments. So these essentially is the U here, okay? So if I know how much dead load to be exerted on a beam, how much live load will be exerted on a beam. So MU for a beam equal to 1.2 self weight plus 1.6 live load from people walking on it, okay? So the bending moment MU equal to the bending moment caused by 1.2 times the dead load and bending moment caused by 1.6 live load. Okay, so right now is a conceptual illustration. We will give you an example tomorrow, Thursday. Okay, we'll give you example on Thursday. So don't panic. Okay, don't panic. Just give you some concept right now. Okay, all right. So that is required strength. So essentially, think about anything related to U, MU, PU, SU, VU, whatever U. That means that's what we expected from loading, from people walking on it, from self weight, whatnot. Okay. But MN, which is the nominal strength, this is come from design. All right. Basically, if I provide so much reinforcement, so much steel in the cross section, I make the concrete member this big. I use this strength. What is the strength of the member? This is MN. Okay. So we have to make sure our nominal strength N is bigger, always bigger or equal than the ultimate strength MU, desired strength MU. Okay. So it's kind of N has to be bigger or equal than U. Okay, again, we'll talk about as through an example in Thursday's lecture. Okay, Thursday's lecture. Okay, all right. So design strengths, right? You need to do the strength reduction factor phi, right? So you need to multiply the phi in front of it. Okay, so afterwards, you need to require that phi nominal strength is bigger than the expected loading from the structures. Okay, so now you have moment for bending, axial force for columns, shear, V is shear, you have the concrete part, you have the steel part, okay, which we'll talk about it. And last but not least, torsion, right? Torsion, T, torsion, okay? So these are the reduction factors, okay? All right, it's a good stop here. I'm gonna stop here today. It's a short lecture today. And on Thursday, we will walk through some examples. So stay tuned, make sure you attend it. And also on Thursday, we'll talk about the chapter 3, which is the materials, okay? So that will cover it. Like I said again, our office hour is usually Tuesday. I'm going to schedule some in-person office hour next week. So you're free to stop by. Of course, I'll be wearing shield and mask and everything. But you know, we can still talk and maybe we can solve some problem if you have any homework issues, okay, homework problems, okay? All right, my friends, this is it. And I do keep an Excel sheet of the question answered, question asked. So that's kind of taken like a part of attendance or bonus points. So if you're like 8 points shy from the target level you want, we can use that to make up for your final grades. And we take turns for questions, but as course develop along, we'll have some volunteering questions. I think that's where we start to see differences. We might have a mini project approaching well, past the first exam. We might have some mini projects, and I haven't set eyes on it. But if we have a mini project, you replace that with one of the homeworks, so you won't have to spend too much effort, okay, on that. All right, I guess that's all. Any questions from us? Any question from you guys? Okay, so I'm gonna stop recording here. Yes.
Professor, I had an issue logging in Zoom, so I was late 5 minutes.
Yeah, I just saw your message. Sorry, but I'll
All right.
okay, thank you for letting me know.
All right. Thank you.
So,